The theme of tonight's video is that when going in a circle, the centripetal force is the net force. And so when you think about finding net force, if we've got like a 2 Newton force up, a 3 Newton force down, and another 1 Newton force down, my net force, F net, is 2 Newtons down. Find the net force. You add them together, including their direction. When we're talking about circles, we go ahead and label the net force the centripetal force. So this force you found here, if that object is traveling in a circle, then that is the centripetal force. And so I want to make that clear, that centripetal force is the net force. And so, of course, they're equal to the same things. The centripetal force is equal to mass times centripetal acceleration, in the same way that F net is equal to ma. Okay, so centripetal force is just the word for the net force when moving in a circle. So same equation, just if circle, we say Fc equals mac. So there can be like 10 different forces that make up the centripetal force because it is the net force. And that's going to be a big theme for tonight. Now what we can do is take the fact that centripetal force equals mass times centripetal acceleration and rewrite that with centripetal acceleration. And centripetal acceleration is v squared over r. So this becomes mv squared over r. And so to summarize the point, the net force is the centripetal force is mv squared over r. So we can find our net force. That is our centripetal force. And that's equal to mass times centripetal acceleration. And centripetal acceleration is mv squared over r. When we were doing net force equation for Newton's second law, we would usually do something like draw a free body diagram. Might have tension up, buoyancy up, and gravity down. And then for the net force, you would write F net equals all the up forces, so Ft plus Fb minus the down forces minus Fg. So sum of the forces. You add them together including the directions. So we're assuming up is positive and down is negative in what I just wrote. And we find the net force, the total force. In a circle, the directions are always changing. So what's up 1 second might be left the next second, might be down the next second. And so an easy way to do this with circles is to say the forces toward the inside of the circle minus the forces toward the outside are the net force, and those are equal to the centripetal force, mass times velocity squared over r. And remember that v squared over r is just acceleration, but it's acceleration for a circle. So in minus out equals ma, or mv squared over r. And by in, I mean forces toward the center of the circle, so forces toward center. And by out, I mean forces away from the center. And if you ever had forces that weren't exactly in or out, you'd have to use sine and cosine to figure out the in and out parts. But that's the basic idea. Forces toward the in minus forces toward the out equal mass times centripetal acceleration, v squared over r. Alright, here's our first example of how we could use this. A ball on the end of the string is revolved at uniform rate in a vertical circle. That means a circle that goes up and down instead of left and right. In a uniform circle of radius 72 centimeters. If its speed is 4 meters per second and its mass is 0.3 kilograms, calculate the tension in the string when the ball is at the top of its path and be at the bottom of the path. So let's activate the way you used to do this, so turn on some prior knowledge in your head. Tension's a force. We're going to use free body diagrams. And we know something's moving in a circle, so there's acceleration. So we're going to use F net. Now we're lucky on this problem. They've already given us the free body diagram. It's right here. At the top of that circle, you've got the string pulling on that ball, and so that string causes a tension. And you've got gravity pulling on that ball, and so that would be our weight force. And we know that ball is accelerating because it's going in a circle. And I'm going to go ahead and encourage you, 1, for points on the AP exam, and 2, just to help you remember what's actually going on here, to say F net for the ball equals mass times acceleration. Okay? And the first question we're going to answer is the ball at the top of the path, so up here. To find the net forces in a circle, we're going to do in forces minus the out forces. And so that is just the F net part. So I want to make sure you get the connection back to Newton's second law. F net is, for a circle, in minus out. And this will be mass times centripetal acceleration, since we're moving in a circle, and that's v squared over r. Now you might wonder, well, can't you have other accelerations besides just toward the center? If the ball were not having the same acceleration toward the center at all points, it wouldn't move in a circle. If it had some acceleration to the left at one point, it would make a circle that curves to the left. So it wouldn't be a circle, it would be more like an ellipse. If it had some acceleration more to the right at one point, it would do something like this, make an ellipse. But to get a circle, you have a constant acceleration just toward the center. And that acceleration is given to you by v squared over r. So net force in minus out equals mv squared over r. So let's do all the forces toward the inside of the circle, and this equation kind of already gives us the signs. It says in is positive and out is negative. Notice that negative there. So the forces toward the inside, I'm going to put them into parentheses because at any time there could be more than one, will be gravity, Fg, and the force of tension. Specifically the force of tension at the top, because we might have one at the bottom. So force of tension at the top. And then I don't see any out forces, so the out just becomes 0. We've got equals m v squared over r. Now ultimately, we want to find the tension at the top. So let's get it by itself by subtracting Fg. So now I've got F tension at the top equals mv squared over r minus Fg. And then tried and true method, let's just go ahead and replace Fg with mg, since that's what it is. So tension at the top equals mv squared over r minus mg. And now I think we're ready to substitute in. So force of tension at the top equals the mass of the thing, which is 0.3 kilograms, times its velocity, 4 meters per second, over the radius, which needs to be in meters, so 0.72 meters. So that's convert to meters. And our 4 on the top does get squared, minus mg, so 0.30 kilograms times 10 newtons per kilogram. Sorry that didn't all fit in one line. So now let's, I'm just going to give up on using this slide again. Let's start multiplying things. So I've got force of tension at the top equals my mass, 0.3 kilograms. 4 squared is 16, so we're going to 16 meters squared per second squared over 0.72 meters minus, I don't want to get this mixed up, 0.3 times 10 would be 3, so minus 3 newtons. So now I've got to do 16 over 0.72, multiply that by 0.3, and subtract 3 newtons. So 16 over 0.72 gives me about 22, times 0.3 gives me 6.67 newtons, and so this all right here came to 6.67 newtons, minus 3 newtons gives me the force of tension at the top is equal to 3.67 newtons. And there's my answer. Clean up this slide so we can now do force of tension at the bottom. Now we're dealing with the ball at the bottom of the path, and they've once again given us the free body diagram. We've got tension pointing up and gravity, force of gravity pointing down. And this is a force problem with centripetal acceleration, so that's F net equals ma. And in the case of a circle, the in forces minus the out forces equals the mass times the centripetal acceleration, v squared over r. Alright, and let's get with it. The in force here, tension's pointing toward the center, so force of tension, and they've called it 2 at the bottom, minus gravity's pointing out here, Fg, equals mv squared over r. So notice whenever if you were to have this situation described to you in words, you need to draw the circle too with your free body diagram so you can see which forces are pointing in and out. So we want tension. We'll add gravity to both sides. Now here, if you're wondering, wait, didn't gravity get subtracted last time? Well, gravity was an in force, and so on the left side of the equation it was added last time. This time it's subtracted, so to get rid of it, we've got to add it. So force of tension 2 equals mv squared over r plus Fg. We can replace Fg with what it is, so now I've got Ft2 equals mv squared over r plus mg. And I've learned my lesson. Let's go ahead and expand it out down here. So let's fill that in. Ft2 equals the mass, 0.30 kilograms, times the velocity squared, 4 meters per second squared, over the radius, 0.72 meters, plus the force of gravity, which we decided last time was 3 newtons. So 0.3 kilograms times 10 newtons per kilogram. So now I should get the same thing I did before. When I multiplied all this out before, I got 6.67. So that's 4 squared becomes 16 meters squared per second squared, divided by 0.72. And again, 16 divided by 0.72. So this part here becomes 22-ish times 0.3, and I get Ft2 equals 6.67 newtons plus 3 newtons, and that gives me 9.67 newtons. So notice that at the bottom of the circle, the string has to pull more because now gravity is working against it, so the string has to hold the ball up and keep it in the circle. Whereas at the top, gravity was helping keep the ball moving toward this, or accelerating toward the center of the circle. And so the tension was less at the top, where gravity was also helping it pull down. And now since gravity is pulling down and the tension is pulling up, the tension has to get bigger to keep that ball moving in a circle. I decided to throw this last question into the PowerPoint because when I first saw this question, it really confused me about what it meant. But the more I thought about it, the more I decided what it had to mean. So let's look at it. And I want to include it because I get to talk through a couple of different things and kind of my process of figuring it out. A person of mass m is riding in a Ferris wheel with radius r. Drive an expression for the maximum speed the Ferris wheel could operate so that gravity holds the person in the ride at the top. So the way I take this is that at the top of the circle, the only force on that person is gravity. That's how I take this question to mean, that there's not some force of tension pulling them back down, or like a downward normal force from like a bar that has to keep them in their seat, that the only force on them is gravity. So if we were to look at our net force and our centripetal acceleration, mv squared over r, the only force would be gravity, Fg. And that's still equal to the centripetal force. And so if it's asking what the maximum speed v is, the only thing that I can think of to do with this question is to solve for that v. And that would give you the v such that only gravity is holding the person at the top. And I think that's what it means. It can't mean that gravity is keeping them from flying up, because there's no force that would cause them to fly up. So this must be what it means. So to solve this, let's go ahead and put in what gravity would be. mg equals mv squared over r. And here, gravity will be positive because in this case, if we did in minus out, gravity is an in force. It points inward, and the in forces are positive. M's cancel, and I get g equals v squared over r, meaning that gr equals v squared. Take the square roots of both sides, and I get v equals the square root of gr. And that was my thought process for this problem, is the only thing it could be asking me is, what do we have to do so that gravity is the only thing holding the person in the seat at the top? I can't think of any other way to solve it. And so I wanted to share that with you, my thought process. Maybe you learned something from the way I thought through it. And yeah, I wondered for a long time, is that really all this question is asking? Because it is a AP level question, but I can't figure out anything else to do with it. The question must mean, how fast do you go so that gravity is the only thing holding you in? And that's it. Have a good night. See you tomorrow.